Hello, everyone. It's great to be here today, albeit remotely. So if you're looking at this video, it must be that I, for whatever reason, couldn't show up on time. I apologize for that. And without further ado, let me start the talk today. Right. So the topic of my talk today is manipulating electrons into the nanostructures. We are interested in multiple 2D material, including graphene, TMDs, and some of the novel 2D materials. And in our lab, we make K-defined nanostructures to try to manipulate the local Hamiltonian towards advance the novel quantum phenomenon and electronic behaviors. And the experiment is done by many of my talented graduate student who is about to graduate, and we have ongoing theory collaborations with many of our theoretical collaborators, and the material, in particular the boron nitride used in this work, is provided by Kenji and Takashi from NIMS in Japan. And this work is supported by National Science Foundation as well as Department of Defense. All right, so okay, so the outline of my talk is two parts. First, I will focus on talking about manipulation of ballistic electron in graphene, one of our recent work using the graphene microcavity to trap the electron and force it to do interference to help with collimation of electron trajectory. And after all of that, if we still have time, I'll briefly mention our ongoing effort of confinement of electrons and manipulation of electrons and optical trains in semiconducting transition metal dicogenites towards quantum bits and the quantum computing platforms. So let me start with part one of this talk, that is the manipulation of ballistic electrons in graphene. So let me start with a general background introduction, right, before for the general audience, right? So Klein tunneling. So what is Klein tunneling? As we know, right, when an electron hits a tunnel barrier, the tunneling probability exponentially decays with the barrier height and barrier weight. However, this applies only to the free electron with a parabolic dispersion relationship. In 1929, Klein obtained a surprising result that when realistic particles with linear dispersion relationship turn through a barrier, the tunneling probability is always 100% independent of the barrier height and barrier weight. Thanks to the linear dispersion relationship and ballistic current flow in the monolayer graphene. And, 2D current physics can be observed if we set up a potential barrier at the center of the graphene devices. For the electrons that are injected perpendicular to the barrier, they turn through with 100% transmission, as expected. However, if the electron is injected with a small incident angle, significant amount of electron will get reflected. This creates a highly collimated electron beam, similar to a laser source in a classical optics, and providing one of the essential building blocks for realizing the electron optics in graphene. Okay, and here another critical component I want to mention is optical lens. When light passes through the boundary of two mediums with different dielectric constant, it refracts because of the difference in group velocity in two medium. So this we all know. In 1967, a physicist Victor Vesalaco published the first theoretical analysis of materials with selective permittivity or permeability, in which the dielectric constant can effectively become selective. As the light passing through the boundary between two materials with positive and negative dielectric constant, it also refracts. But in contrast to the previous case, it refracts with a selective angle, which results into a drastic change of light path. An important implication of this is that light coming from a single point source in the left side of the medium will eventually refocus to a single point in the right side of the medium. In other words, you are effectively creating optical lens with a flat interface. Okay, by applying the gate voltage of opposite sign into adjacent regions in graphene, a p-n junction can be created. Similar to the Sells law, the transverse momentum is conserved when electron pass through a p-n junction in graphene. At the sign of the charge and the effective mass, which the sign across the p-n junction boundary simultaneously, selective refraction is expected, making it possible to demonstrate the Vesalaco lensing in graphene. So many experiment attempts has been conducted to investigate these two concepts. However, both collimation efficiency and Vesalaco coherence are not yet ideal towards a full-scale electron-optic circuit. This limitation prevents the realization of more advanced quantum devices based on electron-optic interference, and the underlying physics stays elusive. So here we will combine the two concepts I just talked about and study gate-tunable Wesson-Lago interference in a low bipolar graphene cavity device architecture that we recently developed. So let me start with this device architecture. It's quite elaborative experimentally, so let me take this slow. So the bottom of the panel on the left is a schematic device image. HBN encapsulated monolayer graphene stack is transferred on top of two atomically flat local bottom gates with a height difference of 8 nanometer and the lateral separation of 50 nanometer. The top part of this panel is a counterplot which maps the carrier density distribution in the device. Uniform P-type and N-type doping are found in regions on top of gate 1 and gate 2, while a uniform p-n junction forms in the cavity between the two gates. Two narrow depletion regions are formed along the boundary of the gates, where significant lattice distortion opens a band gap estimated to be on the order of about 100 milli-electron volts based on the band structure calculation. Above the band structure, there is an optical image of the device. Atomic force microscope 1D scan was also performed. Here, the FM data across the 50 nanometer gap region reveals that the device remains atomically flat on top of both gates as well as in the gap, while the lattice distortion are apparent at the boundary of the both gates. The strain-induced band gap effectively defines two Turner barriers. For carriers with small but finite incident angle theta, these two Turner barriers effectively defines the macrocavity, where the injection rate to the cavity and the loss rate from the cavity are equally low. For large incident angles, each strain-induced barrier provides near-perfect reflections as expected from current turning angle dependence. So when the two local bottom gates are biased at the opposite voltage of equal magnitude, the electrostatically define a p-n junction against the charge neutrality boundary in the center of the cavity. Now, the trajectory of the carrier inside cavity are shown in the color diagram of the first image that we shown on the left. Right after being injected into the cavity with a small incident angle, each carrier inside the cavity first undergoes Wesson-Lago refraction. As the carrier type changes in the middle of the device, gets reflected from the cavity boundary on the opposite side, then undergoes the second Wesson-Lago refraction that ultimately brings the carrier back to its original position. At zero magnetic field, the charge constructively interferes with itself. This results in an increase in measured resistance, as the panel at the bottom right corner shows. Here, N1 and N2 are corresponding to the carrier density in the gate 1 and gate 2 region, respectively. Resistance peaks traces observed only when the carrier density on top of gate 1 and gate 2 are of opposite charge. The absence of this transport feature in the NN and PP gate configuration rules out the possibility for them to arise from disorder of bipolar interference that has been previously reported. Okay, going to the next, we have a rooming picture of these Wesson-Lago interference transport signature that we just talked about, right? So the recent peaks are visible at N1 equal to N2, N1 equal to 4N2, and 4N1 equal to N2, which are corresponding to the red diamond, green square, and blue circles that I have marked here. The following three images below present the carrier density distribution and the trajectory of carrier inside cavity for different cases. In the case of N1 equal to N2, the bold black arrow marks the main interference loop of the first order interference peak as a consequence of two consecutive Wesson-Lago refractions. The faded line marks the trajectory of a smaller portion of the carrier that have reflected at the p-n junction boundaries in the center of the cavity, eventually contributing to the same resistance peak where two consecutive Wesson-Lago refractions to the side of the main loop. Similarly, a closed interference loop can be formed with a sequence of two refractions and one reflections at N1 equal to 4N2 and 4N1 equal to N2, leading to second-order Wesson-Lago interference peaks. Now, to further confirm the nature of the Wesson-Lago interference, we measure the full probe resistance of the cavity under an out-of-plane external magnetic field. At small magnetic field, when B equals to 0.3 Tesla, the Lorentz force prevents carrier injected at a relatively large angle from reaching the charge neutrality boundary and disrupt the interference loop for carrier that do manage to reach the boundary at small incident angle. This results in a broadening of the resistance peak as the new adjusted interference condition differ by specific incident angle. When the second orbit radius becomes comparable to the width of the cavity at B equal to 0.5 Tesla, no injected carrier are expected to reach the charge neutrality boundary and no Wesson-Lago refraction occurs. As a result, the Wesson-Lago interference peaks are fully suppressed The next figure shows the main resistance as a function of magnetic field and carrier density around the peak position, where delta n equals 0 correspond to the peak position. The weight of the interference peak monotonically increases with magnetic field until it completely disappears. Due to the symmetry of the interference loop at N1 equal to N2, no bias dependence is observed for the first order peak. No significant temperature dependence is observed from T equal to 4K to 12K, as the specifics of the interference loop are expected to be insensitive to the thermal excitation. Okay, with that sanity check, we go over its practical application in electron optics. Right. So the angle dependence of the Klein internal improbability has been utilized to coordinate electron flow in ballistic graphene, as we previously talked about. However, carrier with small incident angle can still pass through a series of Klein barriers with a non-negligible probability. This has been the major challenge for further improving collimation efficiency for advanced electron optic circuits. Here it shows that the Wesson-Lago interference can be used to further collimate carrier, particularly those with small incident angle, so the troublesome ones, right? In this slide, the first figure shows the schematic device diagram of the characterizing the collimation efficiency of the Wesson-Lago interference. So source string contacts are intentionally placed at the bottom right and bottom left corner of the graphene on top of the bottom gates. So two 1 micron wide voltage probes are placed at the top and bottom edge of the graphene on top of gate 1. Carriers are injected from the source contact and collimated by the cavity wall, allowing only a small fraction of carriers with small incident angle to enter the cavity. The image on the right is the transverse resistance as a function of N1 and N2. When N1 is smaller than N2, the uncollimated carrier that escape the cavity predominantly reach voltage probe B, resulting in a transverse voltage proportional to the current density from uncollimated charge carriers. At 4 N1 equals to N2, Wesson-Lago interference further localizes this uncollimated carrier in the cavity, resulting in a near zero measure resist transverse voltage, demonstrating its efficiency in further collimating small incident angle carriers that would otherwise manage to get across the cavity. For the two interference peak at N1 equal to 4 N2 and N1 equal to N2, the collimation efficiency is not characterized by transverse voltage, as the ballistic carrier will reach and diffusively scatter from the physical edge of the device before reaching its voltage probe. Now for the sanity check, right, so we show a weak bias dependence is observed for the zero transverse resistance dip as expected from the bias dependence of the second order peaks at N1 equals to 4 N2. As a perpendicular magnetic field is applied beyond B equals to 0.3 testa, the transverse voltage increase both due to the disruption of Wesson-Lago interference as well as the curved trajectory of carriers after passing through the cavity. So no significant temperature dependence is recorded, also consistent with our previous observation and our physics picture. Right, to sum up, like for the previous case, we have developed a low device architecture for microcavity in monolayer graphene with string and electrostatic engineering, right? Like which allowed us to observe the Wesson-Lago interference and use that to collimate our electrons better in monolayer graphene. Okay, so looks like I'm running out of time soon, right? So I'll just go very quickly about the basic take-home messages about this part 2 of the talk, which I wouldn't have the luxury to go into detail. The second part of the talk, I want to briefly talk about the confinement of electron and optical charge in TMD. So I come from a background of gate-defined nanostructure in gallium arsenide and silicon, where we build quantum dot confining a single electron or two to form like a singlet triplet qubit, charge qubit, basically a quantum two-level system that we can design, manipulate, and use it as a basis for the logic component of quantum computing. Right. So things are working out very well in the in this traditional material such as silicon and gallium arsenide, but there's some fundamental technical challenges that we believe that the wonder materials, particularly those semiconducting ones, could provide a solution to it. In particular, those materials you have this beautiful spin valley locked band edges at the for these materials for as long as they are ordinators, right? So the nice thing about those are that, for example, if I define a spin qubit, in order for the spin to relax, since spin is locked to valley, valley also needs to relax. And for as long as you lack this like atomic scale scattering center in the valley, hybridization is harder to happen than that of spin relaxation. So there's reason to believe if we get it to work, overcoming all the technical challenges with these 2D semiconductors, then there's reason to believe we may have more robust qubits based on 2D wonder materials because of this long coherence time and non-relaxation time expected from the vanity degree freedom. So we started this effort back in 2018, where we demonstrate that this is indeed possible to do in 2D semiconductor, despite everybody knows, right, the quality is not quite on par with silicon organic oxide, but perhaps it's already enough. So we've demonstrated that the TMD quantum dot can be formed, and we show like a Coulomb blockade as the typical classical signature of a gate-defined quantum dot. We show the Turner coupling, both in and out of the dot, can be sensitively controlled, and we show that we can manipulate optic trends in this material for the first time, right? So optical trend is something that you can generate with external excitation of a photon that matches with a band gap, right? So if you shine the material with something that with a photon that has a similar energy of the band gap, you will excite temporarily an electron hole pair that is called exciton, and that exciton through dipole coupling can couple to one of the electrons that is originally inside your quantum dot to form a trion state. And in TMD, this is easier to do than that in gallium arsenide silicon because of the large binding energy, and therefore we see this triumphs, and we show that without going into too much detail, we can confine those triumphs, we can manipulate this lifetime, and it's just an extra degree of freedom that we can do in these TMD quantum dot that we can't do in silicon and gallium arsenide quantum dot. So I really have to wrap up my talk. We're also looking at other pin junctions, point junctions, and at the end of the talk, I want to acknowledge my collaborators as well as the funding agency once again. And thank you very much for your attention.